Dr. Myers. Overuse injuries have become increasingly common in high school athletes as both the duration and the intensity of training for sports has increased. There are many different forms of overuse injuries such as stress fractures, ligament, tendon, and muscle strains that often limit an athlete's ability to perform. In response to the increase in overuse injuries in the past decade, many investigations have looked at differences in different running styles in an attempt to minimize risk of these overuse injuries. Some of these different areas of investigation include barefoot versus shod running, heel strike versus forefoot strike running, and stride length variation. While there are many areas where overuse injuries can occur due from stresses of running, I chose to look at those of the lower leg, specifically those of the tibia. I chose to do so because 2 years ago, while participating in high school track and volleyball, I developed a stress fracture in my left tibia. I later found that my injury was a common injury among both running and jumping athletes. Stress fractures are caused by repetitive forces through the bone that overwhelm the body's normal repair mechanisms. Eventually, this leads to microscopic fractures in the bone. The x-ray on the right here is the x-ray of my stress fracture. The area between the two arrows here is an area of bone regrowth over damaged microfragments of bone. In my investigation, I hope to find a way to minimize force to the tibia by hence decreasing the risk of overuse injury. I chose to do so by looking at the differences between heel strike running, contacting the ground first with the heel, and forefoot strike running, contacting the ground first with the forefoot. This led me to the research question, what is the effect of heel strike versus forefoot strike running on the peak deceleration rate of the tibia? I chose to look at deceleration because it will be proportional to the force experienced by the tibia. While many previous investigations have looked at forces using pressure-sensitive pads that measure forces at the foot, my investigation is unique in that it pinpoints the deceleration and related force specifically at the tibia. This led me to the hypothesis that peak deceleration of the tibia will decrease with forefoot strike compared to heel strike running because the ankle and associated muscles and tendons slow down tibia deceleration in forefoot strike while there is more direct force transmission in heel strike. I also looked at the differences at different speeds to allow me to see if faster or slower runners would benefit more from one style of running to another. When looking at different speeds, I hypothesized that as speed increases, the differences in peak deceleration of the tibia between forefoot and heel strike running will increase because the ankle absorbs increasing amount of shock as speed increases in forefoot strike running. For my procedure, I first attached the accelerometer, a device that measures acceleration and deceleration, to the left anterior tibia, the same location as my injury, and secured it with an ACE bandage. I then instructed participants on proper heel strike and forefoot strike running and gave them time to practice around the testing facility and on the treadmill. Using a metronome, I determined the natural cadence for each participant and kept this cadence for both styles of running. Keeping the cadence determined in the previous step, I tested participants for both running styles at 4 miles per hour. Once at the desired speed and cadence, data was collected for 30 seconds. I repeated the above steps for both 6 and 8 miles per hour for all 10 participants. The most important aspect of the procedure of my experiment was to control the way participants run with the exception of how they contact the ground in order to control confounding factors. There was an identical cadence for both running styles to ensure that the stride lengths and steps per minute were the same. All tests were conducted on the same treadmill at a controlled speed, and all participants ran barefoot in order to prevent irregularity from different shock absorptions of different types of shoes. The sample rate on the accelerometer was 400 samples per second, and the placement of the accelerometer was on the left tibia 4 inches up the tibial shaft. For my study population, there were 10 participants in high school between the ages of 14 and 17. There were 5 males and 5 females, all of whom participated regularly in running-related activity. In understanding my methodology, it is important to understand how the accelerometer works. The accelerometer measures changes in acceleration and deceleration of an object in a specific direction. It does not measure speed, but rather changes in speed. Both deceleration and acceleration are measured in the same units, g-forces, that are multiples of the gravitational acceleration, 9.8 meters per second squared. In this investigation, I am looking at the deceleration of the tibia, since the tibia decelerates upon contact with the ground. By measuring deceleration of the tibia, I was able to use Newton's law of motion, which states that when mass stays the same, force is proportional to acceleration. Since I compared the differences in deceleration of the tibia for forefoot and heel strike in all participants, obviously the mass stays the same for each participant. Therefore, the acceleration and deceleration recorded is proportional to the force experienced by the tibia. Since it is the force that goes through the tibia that causes overuse injury, by measuring deceleration, I am indirectly looking at the forces experienced by the tibia. While participants ran, the accelerometer measured in unitless values that were later converted into g-forces. The accelerometer measured 400 times per second, meaning for each trial, for each participant, for each strike style, and each speed, there were 12,000 data points in the 30-second interval. I then identified the peak decelerations for each step. The data table on the left here shows less than 0.1 seconds of data collection. The highlighted value is one peak deceleration recorded for one step. From the original raw data, I converted the values into g-forces. Here is a graphical representation of the 12,000 data points collected for one individual. Using the raw graph as a guide and the raw data to verify, I found the peak decelerations for each strike. Each spike in the data, as shown here, represents a peak deceleration of the tibia for one step. The arrow on the graph here points to one peak deceleration and corresponds with the highlighted value shown on the graph. The table shows some of the peak decelerations for one participant and the times they occurred. For each participant at each speed and each running style, there ended up being around 35 to 40 peak decelerations to be analyzed. Using the peak deceleration extracted from the raw data, I averaged all the peak decelerations for all 10 participants and put the averages into a bar graph. As you can see, the deceleration of the tibia during heel strike, shown in red, was much greater than that of forefoot strike, shown in blue, for every speed recorded. Using a correlated t-test, I compared the heel strike and forefoot strike averages for all 10 participants and generated the p-value shown above each set of bars. All three p-values were below 0.02, showing that there is over 98% confidence in a significant difference between the two running styles. This supported my hypothesis that the deceleration of the tibia is greater with heel strike compared to forefoot strike running style. In order to explain these results, I first looked at the obvious physical differences between the two running styles. With heel strike running, the heel contacts the ground first, followed by the forefoot. In contrast, in forefoot strike running, the forefoot contacts the ground first, and the heel is slowly lowered towards the ground, but does not always contact the ground. From this, I sought an explanation for why there were differences by looking at the anatomy and physiology of the different gait mechanics. In heel strike, the point of impact is the heel. The heel bone, also known as the calcaneus, receives the direct contact. Since the forefoot is lifted upon contact, the relatively weak tibialis anterior contracts and slowly lowers the forefoot to the ground. The impact is transmitted primarily through bone with little dampening of force through muscular contractions. This causes the tibia to decelerate very quickly upon contact. The picture here shows the direction of force in a runner. In contrast, in forefoot strike running, the point of impact is at the forefoot. Upon impact, the powerful calf muscle, the gastrocolius, contracts and slowly lowers the heel and the tibia towards the ground. The force of impact then moves through the forefoot and up the tibia. The slower movement towards the ground and the dampening of action through the gastrocolius muscle contraction causes the deceleration of the tibia to be less in forefoot strike as compared to heel strike running. The picture here shows the dispersal of force in a runner. I also looked at the differences for the two strike styles as speed increased. I graphed the averages for each participant and found a trend line to match the data. The R value generated for each strike style shows that there is over 95% confidence that there is a correlation between increased speed and increased G-forces for both strike styles. However, what was interesting is that the slope for heel strike running was significantly greater than that of forefoot strike running. This illustrates that heel strike becomes increasingly more harmful as speed increases as compared to heel strike running. This also supported my hypothesis that as speed increases, the difference in deceleration between the tibia between heel strike and forefoot strike running also increases. Some of the limitations to my study include that participants were unfamiliar with forefoot strike running. Most individuals, especially when running shod, run heel strike, hence leading to some inconsistencies with familiarity with running. The biggest limitation, however, was that the investigation only looked at the deceleration and associated force of the tibia. While the deceleration and force may decrease at the tibia with forefoot strike running, it may increase at other areas of the body where the deceleration was not reported. This led me to develop the idea for a future study where I would look at the other areas of the body that may receive more contact when forefoot strike running, such as the lower back and the forefoot. The practical application for my study is that since peak deceleration decreased with forefoot strike running, less force is exerted on the tibia, leading to a decreased likelihood of developing overuse injuries such as stress fractures and soft tissue strains. I would like to acknowledge my biology teacher, Kelly Cameron, my qualified scientist, Dr. David Hayes, and Alan Roberts for helping me on background with statistical analysis. And any questions you have now.
I've actually used that little blue shock recorder that you have that works very well. That's a triaxial device, isn't it? So I use 3 axes. One axis you wind up with the tibia. Did you look at the accelerations on the other 2 axes and how did they compare?
I did not. I only looked at the x-axis for the deceleration because I was looking primarily at a compression with a straight load. So the direct force to the tibia is going to be going straight up the x-axis, which is what I measured. The question was if I thought an ACE bandage would lead to any inconsistencies with the data I collected. When using the ACE bandage, I wrapped it pretty tightly around it, but I also attached the accelerometer to the inside of the ACE bandage with tape to further secure it. And there's always possibility that there could have been movement, but since the accelerometer was placed in the same location for both heel strike and forefoot strike for both participants, I don't think this would have led to a lot of inconsistency.
Did you know any qualitative data when surveying your participants?
Well, after participants ran, I interviewed them on how they felt after running to see if it matched with the data I collected from my accelerometer. And when I asked participants, did you find that there was more jarring or impact to your body with forefoot or heel strike, or did it feel the same? 80% of the participants, or 8 out of 10 of the participants, felt that there was more impact to the body with heel strike running compared to forefoot strike running.
I know that a lot of running coaches advise runners to run with a midfoot strike, so hitting the toe and the heel at the same time. How would you expect the tibia's deceleration to be affected if you measured midfoot striking?
The question was, how would I expect there to be differences using a midfoot strike run as compared to heel strike or forefoot strike? Since I didn't look at the data, I can't be sure, but I'm assuming that the averages collected would be in between forefoot strike and heel strike running, making it probably a little bit more force than experience with forefoot strike running, but still less force than with heel strike running.
You showed a slide that had the raw data on it, and right in the middle, it kind of looked like the cadence changed a little bit. Yeah,
This one right here.
yeah.
So the question was, what was the inconsistency, or why did the cadence change here? There is always inconsistencies that the participant may have tripped, or just it's impossible for the participant to keep up a perfect running style throughout the 30 seconds, since no one can run exactly the same. That's my assumption there. I didn't look at it. I didn't look at this particular irregularity compared to the video I collected, but I'm assuming it was a minor trip or inconsistency with keeping up with their cadence.
Why did you choose 30 seconds? And do you think that choosing 30 seconds gave the Forefoot style better advantage than the heel strike style for that shorter period of time? What would you think the endurance level of maintaining the Forefoot strike compared to the heel strike?
So the first question was why I chose to use 30 seconds. I chose to use 30 seconds for one of these reasons, that I didn't want participants to become fatigued over the length of the trial, but I still felt that 30 seconds was long enough to collect data collection, especially since I was able to collect it for 10 different participants. Also, I think the second question was, do I think using it only for 30 seconds gave Forefoot an advantage? And it is possible, because forefoot strike running does use different muscles that many participants don't use on a regular basis, since most people run shod with their when running with shoes. However, since I can't really look at that, I'm assuming since I did it for all participants, it wouldn't have made a big difference.